ask your doubts first. We'll start with doubts. I have given you some questions. Are you able to solve all of them? And if you have any doubt, please feel free to ask. Okay. In that case, let's find out for this question, question number 28. Okay. If a is equals to 1, 2, 2, 2, 1, 2, 2, 2, 1, then you have to find out the value for, I'm writing the expression for which you have to find out the value. So you have to find this a cube. Sorry. So you have to solve this a cube plus a square plus 9a. This is 9a plus 9a minus 7a. We have to find out this value. Okay. Let's solve this question. And whoever is ready to answer, just whoever is done, just raise your hand. But this is for 28. 1, 2, 2, 2, 1, 2, 2, 2, 1. Question number 28. You have to find this a cube plus a square plus 9a minus 7a. Now we know A. First, we should find out A square. Then we should find out A cube. That should be the process. And then just put the values here in the equation. Can somebody verify what is A square? What is A square? Okay. Yeah, Pfizer and Austin both are correct. Good. So this should be 9 to find out A square, everyone. This should be 9, 8, 8, then 8, 9, 8, then 8, 8, 9. First row with first column, 1 square plus 2 square plus 2 square. That would be 9. And first row with second column, so it would be 2 plus 2 plus 4. And first row with third column, again 2 plus 2 plus 4. Sorry, 2 plus 4 plus 2. And then similarly, we will apply the operation on every row, every column. Then A cube would be A cube would be A square into A. So there will be 1, 2, 2, 2, 1, 2, then 2, 2, 1. Have to multiply these two. First row with first column. Do something like this. There must be a pattern in this as well. You have to identify the pattern. Now, can someone tell me the first row of A cube? It's 41. First element is 41. Then correct. 41, 42, 42. Then it should be 42, 41, 42, 42, 42, 41. By just simply observing the patterns of A square, A and A square, you can write A cube. Because everything is going in the same pattern. So the diagonal elements all are same and all the other elements are same. Then A square, A cube will be something like this, similar lines on the similar lines. So you have to observe these patterns. Right now, we don't have anything to do with pattern, but as we progress towards the ending of the chapter, we will see a lot of patterns. So questions like these can be asked where you have to identify patterns, and based on those patterns, you have to find the higher powers. So sometimes what happens is, let's say we have some A. It will be some matrix 2 cross 2 or 3 cross 3, right? And let's say it's a 2 cross 2 matrix. And then they'll ask us something like that find out A to the power 2008, find out A to the power 2009. Or they will give us some expression in which the power will be much higher. Now you are not going to multiply A 2008 times, right? That would not be a rational approach to solve the problem that we are multiplying A 2008 times. Obviously, we don't have to do that. But what we have to do in such type of questions where you cannot identify powers or the powers are greater, right? or where the powers are not given. Sometimes it can also happen like that, a to the power 2n. What does that mean? A to the power even. No, 2n means even, some even number. We are talking about some even number now. So basically, we want to find out what is the power of the matrix. I mean, what is the answer when we take even power of the matrix? Or sometimes maybe odd power of matrix, right? So in these cases, what you have to do is you have to find a, then find a square, find a cube, and at max, you have to go to find a to the power 4, right? After finding out these four powers, in most of the cases, you will get it in 2 times. You will have to only find, I mean, you have to only find a square or mostly a cube. By the time you reach a cube, you will identify what pattern it is following. You have to identify because they will be following some or other pattern. In all such questions where the power of the matrix is a very large one, right? Or the power is vague, we don't have any power. So we have like some numbers, maybe odd number, maybe even number, or maybe number like this, a to the power 4n plus 3. Now, what does this mean? A to the power 4n plus 3. Can you tell me what do you understand by 4n plus 3? Where n is natural number. So if you put n natural number, or let's say n is whole number, if you give values of n, so let's say first value of n is 0. If you put n 0, this becomes a cube. Then if you put n1, it becomes 7. N2, then it's 11. So 4n plus 3 are basically all those numbers which gives remainder 3 while dividing by 4. 4n plus 3 are all those numbers which gives you remainder 3 when divided by 4. So you have to understand these things, that what is the representation, and then how do we find that power. So to find that power, we have to identify the pattern, and to identify the pattern, you need to find out a square, a cube, or at max a to the power 4. In 3 steps, at max, you will get the pattern, and then you have to apply that pattern to that power with which whatever they will ask you. So let's say I'll give you one condition. So we have this a. Now we find out a square, right? And then we find out a cube, right? So after finding out a square, we see that a cube becomes again a. It may be possible that a cube again becomes a. So now any power of a has to answer. Either it will be an odd power or it will be an even power. So for, let's say we have a, something is a, then we find out a square, it is also some other value, right? Then we find out a cube and it becomes a again. Then a to the power 4 becomes a square again. Because when you find out a to the power 4, you just have to multiply both sides by a. So it becomes a to the power 4 becomes a square, right? So all the powers of a can be found out now. How? All the odd powers of a would become a. A to the power 3, a to the power 5, a to the power 7, a to the power again a to the power 9, a to the power 11, all those. Right? And a to the power 2n becomes a square. Now they may ask you some higher powers of a, and you will be able to find that using that pattern. So there may be some questions. If you solve any book other than NCERT, then you will find out such questions in which you have to find out patterns. Right? And that is why we solved this question to identify that they are also forming a pattern. A was also like this, diagonals are same, rest are same. A square is also like this, diagonals are 9, rest are 8. A cube is also like that. Diagonals are 41, right? Diagonals are 41. And then all the rest are 42. Right? Now we can put these values and find out the value of this expression. What is the answer? Can you tell me, someone? If you're solving. So a cube plus a square should be 50, 50, 50, 50, 50, 50. All elements are 50. This sum. Then plus 9a. So this would be 59. Then 68, 68. 68, 59, 68, and then 68, 68, 59. Then minus 7i, final answer should be this. This should be a final answer for this expression. Anji, everybody got that? Can you solve these questions now? Okay. If you have any problem regarding multiplication or matrix polynomial equations type of questions, you can ask me, because after that we will proceed to transpose of a matrix and other things. Also, can I remove this? If somebody's writing, just raise your hand. Cool. So if you're good to go with multiplication, then we are pretty much comfortable in all of the other operations of matrix, because every operation is related to multiplication. Okay. So we were on transpose of a matrix. Let's just brush up what we have understood that day. Like what we mean by when we say transpose of a matrix. So transpose of a matrix means basically we are interchanging rows and columns of a matrix, right? We have talked about it. Change rows with columns, right? So consider A. If you have any matrix A, which is represented by Aij, M cross N, then its transpose will be written as A transpose or A dash, AT or A dash, and it would be AJI, that you have to basically change rows with columns. So I was for rows first and J was for now J will be for rows, I will be for columns, and similarly the order will be N cross N, right? In practical sense, if you understand what we have to do, if you want to find out the transpose of any matrix, just take either columns or rows, take anyone and change it to other. So if you take rows, let's say we want to find out the transpose of this matrix. So I'm taking just rows, one and so first row is 1, 2, or 1, 2. So this would become first column 1, 2. Then second row 3, 4 would become second column 3, 4. Okay. Let's understand some other properties of transpose as well. And also, what can we do with transpose? Yeah, this was the important thing, that diagonal elements remain unchanged after taking transpose. Because see, what are diagonal elements? All the diagonal elements are which belong to same row and same column. So if you change that position, rows with columns, that doesn't change the position of the element, because A11 will be A11 afterwards. A12 will become A21. A12, that is first row second column element, will become second row first column element after taking transpose. But A11 will be A1. Right? So diagonal elements remain unchanged after taking transpose. Right? Now we are talking about some of the properties of transpose. Just so we are on properties of transpose. When we talk about properties of transpose, let's understand with the given example.
Okay, take this example, first one. You can take any example, but let's just take first one because this one is easy to understand. So let's say this is A dash, right? Now, if I want to take its transpose, the transpose of A transpose, so that would be written as A transpose of transpose, transpose of A transpose. Then it will again change the rows to columns. So now the first row is 1, 3. So this will become first column. And second row is 2, 4. So this will become second column. Now this A dash of A dash is similar to A. So what we are basically doing is we're taking transpose twice. So if we are taking transpose twice, first we change row with columns, then again we change row with columns. Basically, we are at the same position where we started. So A dash dash would be A again. Right? This is the first property. Then second property is, so let's say I multiply A with some number. Okay. So let's say I write 2A. A is this. This is very easy to understand. This step. Okay. So first property is A plus B whole dash, but in fact A minus B whole dash. So if you are adding two matrices or maybe subtracting two matrices and taking the whole transpose, it can also be done if you take their individual transpose and apply the same operation. So maybe you are adding two matrices and then taking the transpose. That will also give you the same answer as taking the transpose first and then adding. One interpretation of this is one of the interpretation of this expression. Now the second interpretation is that you can distribute transpose over addition and subtraction directly. Now what do we mean by distributive? Distributive property is this. Now distributive property means, can I distribute 2 with both of them? Or will 2 get distributed when gets inside? Yes. It will be 2 into 3 plus 2 into 6. It means that multiplication is distributed. Okay. Similarly, transpose is distributed over addition and subtraction. Transpose is distributed over addition and subtraction. You can directly distribute it. So if you're adding two matrices and taking the transpose, just take the transpose of every matrix. It may be more number of matrices as well, not just 2. But it is directly distributed. Right? Second property is, if you take transpose of the transpose, it becomes the same matrix again. The third property is, if you multiply a matrix and then take the transpose, it doesn't change the value if you take transpose first and then multiply with the number. That is, you can distribute the transpose over scalar multiplication. Now this is scalar multiplication. Because k here is some number. So this is scalar multiplication. You can distribute transpose over scalar multiplication as well. But scalar multiplication, I mean, there would be no transpose of k, right? I mean, how can you change? What is 2 transpose? 2, nothing. Because this is not a matrix. Transpose is for matrix. But what does transpose do to a matrix? It will interchange rows and columns. But for 2, it can't change rows and columns. Because there are no row and no column involved in this. Okay. So the transpose will get distributed directly. Transpose will get distributed directly. Okay. Now the fourth property, the most important. See, transpose was distributive over addition and subtraction, but it is not the case over multiplication. Now, as we understood the multiplication now, we have a lot of properties related to multiplication. So I have already told you that multiplication is the most important property in matrices. So we have a lot of properties based on multiplication, but all the properties will go in same way. You have to remember this pattern. So whenever we distribute anything on multiplication in matrices, let's say you multiply two matrices, but after multiplication, you want to do some other operation as well. Like in this case, you want to multiply A and B, and then A wants to take its transpose. So whenever any operation is multiplied on multiplication in matrices, the order of the matrices gets lost. So we can distribute this, no worries. But after its distribution, the order will get changed. So B dash into A dash. AB whole transpose is equal to B dash A dash. Right? This is the important part. Or rather, this is an important pattern. Everything will go like this. So we will apply some other patterns as well on AB. Okay, let's say this is inverse. This is AB inverse. We'll talk about inverse. That will also be B inverse into A inverse. So most of the things, most of the operations are distributive in case of multiplication as well. But when we do when we distribute them on multiplication, the order gets reversed. This is the thing to remember. Okay. While in addition and subtraction, there is no question of order. You can take either B dash or A dash because that will also provide you the same answer. I mean B dash plus minus A. No, in case of minus, good. But in case of positive, that will be the same. But here, all the operations in multiplication of matrices get serious. Just remember this. You can also verify them using some examples. You want to get, but let's not. We can do that
at home. So and that will be very easy to verify. Take any one matrix, whatever you want, take any matrix and apply these all operations. So what you can do is take any matrix A, 1, 2, 3, 4, let's say, and take any matrix B, which is, let's say, -7, -10, 4, and 0, and apply these values on left hand side and right hand side, or you can apply on both, I mean, you can apply all the properties. Right. Let's solve some questions on this. Oh, we'll also have to verify some of the questions are for verification. Let's solve this one.
But these questions will not be asked in. They are very easy questions. They will not be asked in those. So your teacher may ask them in your examination, these midterm or test, but they won't be asked in exam. You can see the board exam because these are very easy questions. But let's solve one of the questions. So we are given A. Let's say A sum 4, 7, 8, or 4 minus 7 and 8, and B is, sorry, what should be the order of B? Can someone tell me what should be the order of B? Yes, guys, what should be the order of B? No, tough. 2 into 3. 2. Okay, 2 into 2. Who answered this? 2 cross 2. Hiram? Hiram, what's the order of A? Tell me this. A, order of A is 3 cross 1, right? So the order of B should be, if you want to multiply A and B, what should be the order of A and B? I mean, what should be the order of B?
Sir, I'm so sorry. I thought the above example you did.
It's okay. Now tell me, what should be the order of B if you want to multiply A and B?
Order of B should be 1 cross something. Because if you want to multiply A and B, then number of columns of A must be equal to number of rows of B. So it can be anything, 1 cross something, but I am taking 1 cross 3. So this should be -1, 2, and -3. Now you have to verify AB whole dash is equal to B dash into A dash. AB whole dash is equals to B dash A dash. You don't have to do much. Let's take left hand side. Then we'll find out AB. So AB would be what? 4 minus 7, 8 into -1, 2, and -3. So first row, first column. First row, first column will be what would be the order of the multiplication? That is order of AB, 3 cross 3, right? Because it's 3 cross 1 and 1 cross 3. That should be 3 cross 3. First row with first column, so that should be -4. First row with second column, 8, -2. Second row with first column, 7, -14, 21, then -8, 16, and -20. That should be AB. Hence, AB bar would be, or AB transpose would be, so the transpose would be, first row will be -4, or first column will be -4, 8 and -12, 7, -14 and 21, then -8, 16 and -20. So this is my equation 1 because I have found out AB dash. Now I will solve RHS. First I will find out B dash, then I will find out A dash. So B dash would be what? -1, 2, -3, and this would be a column vector. So this is a row vector B. This would be -1, 2, and -3. And then A would be a row vector, which would be 4, -7, and 8. And now you can see, if we would have distributed it directly, then we would not be able to multiply A dash and B dash. We can only multiply B dash A dash, not A dash B dash A. A dash B dash is not possible to calculate. No. Right? So B dash A dash should be first row, first column. First row, first column, which should be -4, 7, -8. See, -4, 7, -8. Then second row, first column would be 8. Second row, second column would be -14, and then 6. This would be -12, 21, -24. That should exactly be the same. From first and second, you can say that AB whole dash is equals to B dash A dash. That is the way you can approach these questions. And these will be easy just based on the multiplication. If you can multiply two matrices and you know how to take transpose, you'll be good to do these type of questions. They will not be asked in board exams though. So what is important for board exams? Yes, this. We have other type of matrices as well, not just these. You understood these row matrices and column matrices. These were the basic type of matrices. Basically, we want to introduce matrices to you. So we told you the basic properties of matrices and types of matrices based on those basic properties, right? And we tried to explain you the algebra behind matrices, then transpose of the matrices, right? Now we know what operations can be applied, right? It's simple, basic four out of four mathematical operations, we can apply three. We cannot divide two matrices, but we can always add, subtract, and multiply two matrices, right? We know how does a matrix look like, and we know about diagonal elements. We know about basic representation. We know about how to take transpose. Now, after this point, whatever goes will be based on all these properties, and will be an extension of all these properties which we have understood. Right? So anything which we are going to find out now will be based on all of these properties which we have understood. So if you have any doubt, please feel free to ask, because you won't be able to do well if you don't know these things which we have discussed here. Or if you have any doubt while we will be discussing this, you can ask me. So now we are talking about two types of matrices now, symmetric and skew symmetric. Holds a great importance, can be very useful. We have different types of matrices also. You don't think about it that we just have these two types of matrices. We have kind of 50 to 60 kind of matrices. We won't be studying them all, but there is a lot of kind of matrices, because you can see the data is, we have a lot of data, right? We have to apply, we have to extract information from that data, and we should know how to handle the data. And to handle the data, matrix is the best thing which we have. So we have a lot of use of matrices in Excel and machine learning and different kind of algorithms used in different languages. So that is why we have a lot of kind of matrices, right? Now these two are important. One of the two important matrices, very important pair of matrices, symmetric and skew symmetric. Now, what are these? First of all, we will discuss about what are these symmetric and skew symmetric matrices. So some matrices are like that. So let's say we have some matrix which is A, and its element is Aij, and this is a square matrix. Now, first of all, symmetric, either we are talking about symmetric matrices or we are talking about skew symmetric matrices. They must be square. Why? You will get to know that. But let's just take this for square for now. You'll understand why did I take square. Okay. No, and I also told you that most of the application matrices are applied on square matrices only. Right? So we will be talking about square matrices from now onwards, mostly. Consider A is equals to Aij n cross n. So this is a square matrix A. Then A is called a symmetric matrix if A dash is equals to A. This is the important thing. So if you take the transpose of the matrix, right? You take the transpose of the matrix, and the transpose of the matrix gives you the same matrix again. Then this matrix is known as symmetric. Now let's understand why this is called symmetric and why this has to be a square matrix. Let's take a matrix. I'll show you one symmetric matrix first. So this is a symmetric matrix. Let's see how. So A dash will be first row will be first row is 0, 1 in A. First column would be 0, 1 in A dash. Then second row in A is 1, 3. So this will become 1, 3. Now see, A and A dash both are same. Hence it is called symmetric matrix. Right now this A matrix is symmetric. Now why is that? You understood this? Because I hope you understood, because if we take the transpose of any matrix and it gives you the same matrix, then it is called symmetric. This is the simple mathematical logic. Now let's understand the interpretation. How is this happening? So why did we call it symmetric first? In case of symmetric matrices, non-diagonal elements would be divided in two parts. So we have talked about this, that any matrix can be divided into three parts. One is diagonal elements, right? Second is upper diagonal elements, and third is lower diagonal elements, right? Let's see one basic matrix, basic representation. So this is A21, A22, A21. Every square matrix, I would like to modify this statement. Every square matrix can be divided into these three types of elements. One is this. Okay. Now another are these. And these two. So these are upper diagonal elements, sorry, upper triangular elements. Then these are diagonal elements, right? And then this is lower diagonal elements, lower triangular elements. Let's understand what is happening in A dash. So when we find out A dash, the position of these diagonal elements for a square matrix, we are talking about first class matrices only because they are the most important. We will only discuss these matrices. So all the diagonal elements remain unchanged. When we take transpose, all the diagonal elements remain unchanged. All the upper triangular elements becomes lower triangular elements, and all the lower triangular elements becomes upper triangular elements. Right? A13, transpose of A13 would be A31. A12 would be A21. Now this A23 would be A32. Simple. So upper triangular elements will become lower triangular elements, right? Now we are calling it symmetric because all the upper triangular elements are just similar to lower triangular elements. A12 would be equal to A21. Then only it would be the same matrix. If we have this one, let's say this value is 1 and this value is 2, no, this will never be a symmetric matrix. Why? Because after taking transpose, 2 will be here and 1 will be here. These two have to be same. These two have to be same. These two have to be same. So calling it a symmetric matrix. So in case of symmetric matrix, your A dash becomes A. And now what is A dash? For A, if A is Aij n cross n, then A dash will be what? Aji n cross n. And if A is equals to A dash, in that case, Aij is equals to Aji. We can also prove it mathematically, whatever I try to tell you. But you can also see it physically. If they have to be equal, then only your matrix will be symmetric. But by mathematically, we can prove this because A is Aij, A dash would be Aj. If A is equals to A dash, then this means Aij is equals to Aj. So a matrix symmetric when its transpose is equal to the same matrix. And this will also look like symmetry. Now let's understand one matrix. So diagonal elements can take any value. They will get, I mean, they won't be changed. Right? They can take any value, put anything. If you want to write a symmetric matrix yourself, how do you write it? I'm telling you. So you can take any diagonal elements, whatever, 3, 4, 10. Only a square matrix can be symmetric, that you know. And also why a square matrix? If A is n cross n, let's say, then A dash would be n cross n. How can they be equal if the order is not same? So they have to be square, right? Okay, so I'm writing a 3 cross 3 symmetric matrix. So I can choose any value for diagonal.
Now, if I take any value for this, whatever I take here, I have to take here that value. So let's say I take here √3. Then this is √3 fix. Let's say I take 7 here. I can choose anything for here, but the value remains same at this place as well. I can take anything here, anything, whatever I want. What? -10. So then it has to be -10 here. These two, and these two has to be same. Right? That is how you can write a symmetric matrix. Symmetric matrix will look like symmetric. About the diagonal, it will be symmetric. About the diagonal, it will be symmetric. Anji, everybody understood what is symmetric matrix? Okay, let's talk about skew symmetric as well. Skew symmetric is basic. If you understood symmetric, you have already understood skew symmetric. So the simple rule is this, that let's say I have some matrix A, and this is Aij, right? This also has to be square. You will get it by. Then A is said to be skew symmetric if A dash is equals to negative times of. The only difference is it should be negative times of. Then it can be said a skew symmetric matrix. Now let's apply some maths. So we are saying A is this. It means that A dash has to be Aj. Right? Now we are saying, what we are saying here is A dash must be equal to -A. If A dash equal to -A, then we can I say that Aj must be equal to minus times of Aij? Going purely mathematically, nothing very fancy. If A dash is equals to -A, then it should be equal to this. Aj must be equal to minus times of Aij. You can, I mean, this is just for matrices symbol, but we know we are comparing the elements only. So you can also write Aj is equals to minus times of Aij. That is the rule. For skew symmetric matrix. Now let's see one example. How does a skew symmetric matrix look like? This has to be square. This property right here gives us something very interesting. Okay. What? Before writing the example for skew symmetric, I think I should do this. Let's go with the property. Let's try to find out the diagonal elements for a skew symmetric matrix. Okay. Yeah. So we are talking about diagonal elements of skew symmetric matrix. Okay, so guys, I have few questions for all of you. Please answer these questions. Okay. First of all, how do you represent a diagonal element? How do you tell me what is a diagonal element? Any one of you can tell me the answer. Feel free. What is a diagonal element? Good. Yes, Faisal, correct. So father has told us that Aij, where I equals j, right? Which is the absolute correct definition of a diagonal element. That diagonal element is that in which I is equals to j. Or physical interpretation के लिए we understand this by that the element which belongs to same row and same column. So it can be A11, A22, A33, A44, or something like that for a square matrix only. Right? Always remember the diagonal elements only exist in case of square matrix. Okay? So if I want to find out the diagonal element, what I will do, I will put I and j equal. So I want to find out diagonal elements of a skew symmetric matrix. Let's say this is a skew symmetric matrix. Some matrix, this whatever we were talking about, this matrix was skew symmetric. Right? Then AJI must be equal to minus times of AIJ. Now I want to find out the diagonal elements. So what I'm doing is basically put I is equals to j in this equation, maybe. So if you put I is equals to j, not maybe I mean I have to put I is equals to j in this equation. Then I can find out, or I can find something interesting about these elements. So if I put I is equals to j, so I can replace j with I or I with j. So let's make one variable. So I'm replacing j with I. So this will become AII is equals to minus times of AII. Right? It means that twice of AII is equals to 0. It means that AII is equals to 0. What does that mean? All the diagonal elements this is a very important result. All the diagonal elements of a symmetric matrix are 0. How? Mathematically, I showed you how. Mathematically, if I want to find out diagonal elements, I would put I and j equal. Right? I would try to equate this equation. I mean, I will try to check this in this equation. So I put I is equals to j in this equation, which was the condition for skew symmetric matrix. And by that condition, we find out that all the diagonal elements of a skew symmetric must be 0. Now let's understand it physically events through a matrix, through an example. So I'm taking a skew symmetric matrix only, so I know this has to be 0. But you don't know it. We'll check this. Now let's talk about upper triangular elements. You can take any upper triangular elements, right? Or any lower triangular element. Choose one, either from the two, choose one which you want to take. So let's say here for this and this position, for this and this position, I'm taking this -4. So this has to be 4. For a symmetric matrix, remember, if this was -4, this has to be -4. But for a skew symmetric matrix, if this is -4, this has to be 4 because they are negative times. I mean, this time they are correlated as negative times of one another, not equal. Negative times of one another. Absolute value is same, but the sign has to be different. So for these two, I'm taking this. So I'm taking this 2. So this, or I'm taking this -2. So this has to be 2. And here I'm taking √3. So this has to be -√3. Now let's find out A dash. In this case, A dash is 0 -2 4. Then 2 0 √3. Second row is 2 0 √3. So second column is 2 0 √3. Then third row is -4, -√3 and 0. So if this is A, this is A dash. Now let's compare them. Whether A dash is equals to -A or not. So for -A, if I find out -A, I just have to multiply all the elements with -1. Okay? So this would be 0, 2, -4, 0, 2, -4. Multiply this with negative. -2, 0, -√3. Now come to A dash, -2, 0, -√3. Multiply this with third row of A with -4, √3, 0. Again, 4, √3, 0. So this is a skew symmetric matrix, first of all. And I'm sure you must have understood the logic of minus times as well. Because this has to come here, right? So if they are related to minus times, then these two elements should be related to minus times of each other. Now, what are we saying? We are saying that A dash is equals to minus A. If A dash is equals to minus A, then consider about diagonal elements once. Diagonal elements won't change their position. They will remain same. So A11 previously will remain A11 in A dash as well. Now we are saying that A dash and A are related to minus times of each other. This means that A11 has to be minus times of A11. No. If A dash is equals to minus A, then every diagonal elements must be equal to its negative times as well. Because they are not changing position. They are there. A11 is at A11. So when you find out A dash, A11 is there at the same position where A11 was in A. Now you are saying that they are related to minus times of each other. That is A11 has to be equals to minus times of A11. That is only possible when A11 is 0. A number is equals to its negative self when it is 0. In all other cases, 4 is not equal to minus 4. 11 is not equal to minus 11. Only 0 is equal to minus 0 because minus 0 is same 0. So all the diagonal elements must be 0 because they are not changing their position. And in case of skew symmetric, you are saying that A and A dash are negative times of each other. That's only possible when the diagonal elements are 0. Right? And all the non-diagonal elements are related to such that upper triangular and lower triangular are negative times of each other. While in symmetric, upper triangular should be symmetric to lower triangular. Aij must be equal to Aj. Right? Chaliye. Now let's consider one of the important property. What can we do with symmetric and skew symmetric? See, we can, I mean, what? We can compute the multiplication of two matrices in way less calculation, or the multiplication of two matrices will be much lesser calculated as compared to a multiplication of normal two matrices. If the matrices are symmetric or skew symmetric, their multiplication, their powers, all the operations are very easy to operate on these matrices because they are forming a pattern. Simple. If they are forming a pattern, we can find out these powers very easy. If they are forming a pattern. If they are not forming a pattern, the powers, I mean, to find out all the powers will be tough, first of all. So what we do is, our motive is that to reduce all the calculations, we should break our matrix into a symmetric and skew symmetric matrix. So can we do that? First question is this. Yes, we can do that. We can easily reduce our calculations in matrices by just changing them to some specific matrix. So we can change every square matrix. We can change every square matrix into a sum of symmetric and skew symmetric. That is the first property, first of all. Now, to understand if a matrix is symmetric, what will you do? So let's say I give you one matrix. I ask you whether it is symmetric or not. What will you do? Okay. Just wait, I'll frame my question in a better way. I'll give you one question. Tell me whether this is symmetric or not. Is it a symmetric matrix or a skew symmetric matrix? Everybody has to participate in this. Mahmoudi, is it symmetric? Yes or no?
Yes, sir.
It is symmetric. How did you find out?
Because it's not skew symmetric.
So a matrix has to be either symmetric or skew symmetric. A normal matrix can also be there. No.
Yes, sir.
So is this symmetric? How will you check whether a matrix is symmetric or not? I will take its transpose. Namuddin, I will do this. I'll take its transpose. So 1, 2, 3 will become 1, 2, 3. First row will become first column, then 2, 4, 1, then 3, minus 1, 0. And I will check whether they are same or not. Are they same? No, this is my question to you. Are they same?
No.
No, right? So this is not symmetric. Are they minus times of each other? If you multiply one of the matrix with minus, then can they be equal?
Yes, sir.
I mean, if you multiply a with minus, then a dash will be equal to minus a. I don't think so.
Yes.
No. Okay, minus a would be what? Shall tell me. Solve this. Kya hoga
No,
minus
no,
A?
no. It won't be.
No,
Sorry.
yeah. Because every element will get multiplied with minus, right? So to check whether a matrix is symmetric or skew symmetric, what we do is we just simply take its transpose and check whether we got the same matrix or not. Simple. Okay. If we have the matrix, the values of the matrix, then it is also very, I mean, it is much easier to find out actually. How? You just have to check whether these two are equal or not. See, here they are equal, but here they are not, and this is not symmetric, right? So if the matrix is given, just simply check it by the rule. And if it's not given, then you will have to take transpose. Now, how will you take transpose? I'll show you how will you take transpose. I'll give you one example, but first you identify. So this is neither symmetric, right? Nor skew symmetric. Now let's talk about this. Is it symmetric or skew symmetric? Austin, is it symmetric or skew symmetric?
It's not symmetric.
It's not symmetric. Okay, what about skew symmetricity? Is it
Um,
skew symmetric? Feel free to answer, don't worry. The max is that you can only give the wrong answer, don't worry. Is it skew symmetric? How do you check skew symmetric? Just compare these two elements. Either compare these two elements or take a dash and then compare, right? So how do you do this first? You tell me.
You take the transpose.
Yeah. And after taking transpose, are they equal?
Yeah, yeah. I mean, they're not equal. The signs are exchanged.
Signs are exchanged. So they may be equal. No? Okay, Faiza. Yes, Faiza, you are wrong, but I expected this answer. So okay, in the first, when in the first site, when what we observe is that these two elements, 1 and minus 1, 2 and minus 2, 3 and minus 3, they both are negative times of each other, right? And that is what we were saying for skew symmetric, that for symmetric they must be equal. These three pairs must be equal, and they can be anything. But for skew symmetric, these three pairs must be negative times of each other, which is happening in this case, right? But there was also one condition, one more condition, that all the diagonal elements must be zero. Now, in this case, all the diagonal elements are not zero. So if you take A dash, let's find out A dash. So 1 minus 1, 2. Then 1, 2, 3. Then minus 2, minus 3, 3. And if you take minus A dash, this will be minus 1, plus 2, plus 1, minus 2, plus 3, minus, minus, minus. Now check whether minus A dash and A are equal or not. See, first check all the non-diagonal elements. All the non-diagonal elements are equal. All the non-diagonal elements are following the conditions, but they are not equal just because of diagonal elements. Diagonal elements in first case is 1, 2, 3. In A is 1, 2, 3, and then diagonal elements in minus A dash is minus 1, minus 2, minus 3. It should be 1, 2, and 3 if they have to be skew symmetric. But they can never be skew symmetric because the diagonal elements are 1, 2, 3, and 1, 2, 3 will not be equal to minus 1, minus 2, minus 3. 0, 0, 0 will equal to minus 0, minus 0, minus 0. Right? So A is not equal to minus A dash, hence neither symmetric, ना ही तो A minus A dash के equal है, ना ही A dash के equal है. So they are neither symmetric nor skew symmetric. Austin, did you understand this? How to find out symmetric and skew symmetric?
Yes.
If the matrix is given, just check directly the pairs. If it's not given, then we have no other option than by checking it with the given condition. The condition was any matrix is symmetric if its transpose is same as that of matrix, and any matrix is skew symmetric if its transpose is negative time of the original matrix. Can you see? No, diagonals of the transpose should not be equal. I mean, diagonal elements of the transpose must be equal to the diagonal elements of the matrix, simple matrix, because diagonal elements are not changed. In A as well as A dash, diagonal elements remain same. So if you are saying that a matrix is skew symmetric, then its diagonal elements must be equals to its minus times of the same diagonal elements. That is, A11 has to be minus times of A11, which is only possible when A11 is 0. So all the diagonal elements must be 0 for a skew symmetric matrix. Do you understand it, Faisal? Now what are we saying? Just hear me out first. Okay, I'll show you one more example. Two more examples. From the original matrix, so let's see. I'm going to write a symmetric matrix. And if I write minus 1 here, minus 1, 3, 3, minus 10, minus 10. Now this is a symmetric matrix. You can also check. For simple check, just these two pairs, 3 pairs. This is minus 1, this is also minus 1, this is 3, this is 3, this is minus 10, this is also minus 10. And diagonal elements can be anything. So this is symmetric. For skew symmetric, we know diagonal elements must be 0. Whatever is written here, minus sign should be written here. Whatever is written here, minus sign should be written here. Whatever is written here, minus sign should be here. So this is skew symmetric. And also check that by finding out A and A dash. Right now, let's hear about the important property. What is the use of this? How did we start talking about symmetric and skew symmetric matrices?
It's just.
Guys, sorry. Yeah. So let's talk about why did we start talking about symmetric and skew symmetric matrices. So every square matrix, this is very important for you know. Every square matrix A every square matrix A can be written as a sum of a symmetric and a skew symmetric matrix. Now, what do we want to say by this is that let's say we have this matrix, square matrix A. Okay. Let's consider A. Yes, so consider A, let's say we have this matrix A, then it can be written as a sum of a symmetric and a skew symmetric matrix. Then A can be written as A is equals to half of A plus A transpose plus half of A minus A transpose. Now the question from transpose will be from here, based on this formula. First of all, this is a symmetric matrix. G. So this A can be written as half of A plus A transpose and half of A minus A transpose. So this half of A plus A transpose would be symmetric. And this would be skew symmetric. Now let's understand how is this symmetric. How did we know that A plus A transpose is symmetric? If a matrix is symmetric, then we can check that by taking the transpose of it. So let's say if I'm saying that A plus A transpose is symmetric, yes. So I want to check whether this matrix A plus A transpose is symmetric or not. If this is symmetric, then multiplying by half doesn't change the fact that this is a symmetric matrix. We can multiply by any scalar quantity we can multiply any symmetric matrix with a scalar quantity. It will not change the nature of that matrix. The matrix will remain a symmetric matrix. So A plus A transpose is a symmetric matrix. Now, how do we check that? So let this A plus A transpose is some other matrix B. So A and A transpose will, after adding up, will give us some matrix, and I'm naming that matrix as B. So I'm saying that B is a symmetric matrix. If B is a symmetric matrix, then it will only be possible if B dash is equals to B, right? So I just told you when we were finding out the symmetric and skew symmetric matrices, the examples, we were checking the examples. Then I told you that to check a symmetric matrix or to check a skew symmetric matrix, we have to take the transpose of that matrix and then compare with the original matrix. If the transpose and original matrix is same, then it's symmetric. If they are negative terms of each other, then it's skew symmetric. And if it doesn't follow any of the two conditions, then it's neither symmetric nor skew symmetric, right? So I'm saying that A plus A transpose is a symmetric matrix. I'm considering A plus A transpose as B, which is a symmetric matrix. Now, why? Let's check whether B is symmetric or not. So I'm taking the transpose of B. So B dash would be A plus A transpose dash, right? So be A plus A transpose whole dash. Now transpose is distributive. Transpose is distributive over addition. So this is A dash. This will become A dash plus A dash of dash, which is nothing but A dash plus A. And A dash plus A is nothing but B. Right? So this A plus A dash comes again A dash plus A after taking transpose. So we can say that B dash is equals to B. Hence, A plus A transpose, if we add a matrix to its transpose, then it would become a symmetric matrix. Similarly, if we subtract the transpose of a matrix from the matrix, then it will become skew symmetric. Just check that fact out as well. We've already established that A plus A dash is a symmetric matrix. Now let's check for, let's take this as C matrix, A minus A dash. Then C dash would be A minus A dash whole dash. And this would be A dash minus A dash of dash, which would be A dash minus A. Right? After taking negative common, this becomes A minus A dash again, which was C. So C dash is equal to minus C. Hence, to check any matrix is symmetric or skew symmetric, just take the transpose. So A minus A dash is a skew symmetric matrix and A plus A dash is a symmetric matrix. Every square matrix can be written into the sum of these two. Now, if I write this sum, you can check this. If I multiply with half, this is half A plus half A transpose. Then this would be half A minus half A transpose. So transpose wala part will get cancelled out and half A plus half A will be A. This is symmetric, this is skew symmetric. So every matrix can be written like this. We have to actually write a matrix into form of this. So we'll use this in, I guess, yeah, we have trust model. So in the next class, we'll solve some questions on this, but this is the most important property related to symmetric and skew symmetric and transpose of a matrix. You can get a question from this. So we'll practice this part. You can ask me a doubt if you have any. Otherwise, just stay for the test, please, assessment test. And I hope if you haven't completed the question up to 3.2 exercise, then please do it. Solve the given questions. And we will, from the assignment, I'll give you questions in the next class. But complete, and some of the part of 3.3 as well completed. You can do.